Good afternoon, everyone. Welcome to the September edition of the Passive House Alberta Coffee Talk. My name is Frank Crawford, and I am the Education Committee Lead with Passive House Alberta. And today we are here talking with Edmund and his wonderful net zero FIAS certified home near Canmore. So I won't add anything else to that, Edmund. Why don't you take it away and tell us more about your lovely house? If there's any questions, put them in the chat box, and we'll leave the questions to the end.
Well, that's fantastic. Thank you so much, Frank. And thank you, everyone at Passive House Alberta, for inviting me to this. So this is a photo of the house under construction. This is as of about a week or two ago. So we're taking along not too bad. We're into mechanicals now. But I'll get going here. I'm going to stop my video just because I unexpectedly find myself on hotel Wi-Fi. And hopefully that won't stress it too much. Just as we get going here. Let's see if this will let me. There we go. I just want to say a big thanks to Kim at Bocro Design and Raf and Rainey and Robert at HSS Design Build, our builders, and the whole crew over at Collective Carpentry who did all of our offsite panelized construction. Starting off, so our project goals with this, I remember writing in a narrative years ago at this point that we were hoping to have it be not a dumpster fire for the environment. Exactly what that meant took a bit of figuring out. But the goals with this, it's our long-term home. And we kind of discovered that anything that we wanted to be better than code built would end up having to be custom built effectively. It's not something we can go and buy on the market. And if we want a custom built home with a builder that we can choose, we basically have to build single detached. And so that's what we ended up doing. Yeah. Here. There we go. We've gotten a lot of questions about why go passive house, and I think that's a good one. There's kind of this big realm between code built and passive house. And in that space, we find things like R2000 and LEED and Built Green and Pretty Good House, and now tier code, step code, which is a really appealing option that we didn't really have when we first started this out. And I think what we found is that a lot of those are either kind of deprecated, like R2000. I can't find anyone building that or thinking about that a whole lot anymore. Some of the other ones are mostly points-based systems. There's appeal of Passive House being a performance-based system. And Pretty Good House is a really great conceptual model. But as someone who's not in the building space myself, it's a little difficult to have the confidence that I'd be catching everything and thinking of all the things that you're supposed to think about there. So that's what ended up leading us to Passive House. Another big part of that was third-party verification. My background's in the research sciences, so third-party verification basically sounds like peer review to me. And that sounds great, having someone else who's familiar with this and familiar with the standard, look at the product and look at the design and basically validate it. Because that's not something that I felt that I was particularly qualified to do, especially a lot of the small details. So I can think about high level things. I've read the books, but does this particular window detail make sense? Will it work? That's not something that I was really confident in. So we'll go back and right. And the last one is FI versus FIAS. So if we're looking at Passive House, at this point, my general understanding of FI versus FIAS is that it is a philosophical difference of whether there is a standard or whether there is a climate adaptive standard. And I just found myself slightly drawn to the thinking of FIAS somewhat more than FI, but I think both are good. So when we're searching for a lot, we did all the usual things when you look for a lot. Where is it, views, that kind of nice stuff. But we did find ourselves somewhat constrained by wanting to build a higher performance, and wanting to build Passive House, because that meant bringing our own builder to it. And finding a lot without a builder attached means that you're basically dependent on resale market. Any new layout developments will generally have builder commitments there. Um, so we started looking around at what's available in the resale market. We are looking around up in Canmore, and we had a smattering of choices, which is fairly representative of what often shows up on and off the market. We were particularly looking for solar exposure, as you kind of expect. And we found that a lot of lots have poor solar orientation because it was never something that was considered when the development was laid out. And many lots have lot adjacent or on-lot trees that may not be removed, and those are protected either by being off-lot and on someone else's property, or oftentimes on-lot restrictive covenants would prevent you from removing trees in order to protect the viewscapes of adjacent uses. So we eventually went around, took photos facing south of all of these places, and kind of see a lot of what we were dealing with here. This is also Canmore, so we're dealing with a lot of hills and slopes and a lot of trees. And there's a fairly clear winner that emerged from this process. However, and this is what we went with, but this site comes with some baggage. So just for context, Canmore is about an hour and a half outside of Calgary, up in the mountains. It's located in the Bow Valley along the CP rail line, which is what first led to modern settlements in the area. And the reason why Canmore became a thing is that they found coal here. So here you can see a view of Canmore, of the Bow Valley, and you can see the site that we have with a little red arrow down on the right next to a big open field. This is great for solar exposure, and if we look at it from an aerial view, there are a lot of appealing things about this, but you might ask, why is there this big open field in a kirk of the Bow Valley? Well, this is what that site used to look like. On the left, Canmore Museum figures that's in the 20s or the 30s based on the car there. On the right, that's probably in the 60s or the 70s. So this was the site of the Canmore #2 coal mine and the tipple, which is the big structure you see there, which is what they used to load coal into rail cars. So that blue arrow there is where our site is, right about under that boxcar full of coal. Here's a view of the site from, I believe this is 1967, and you can just barely see faintly outlined the roads of the current subdivision. And the blue arrows indicating where our site is, right under the spur line carrying coal trains to and from the tipple for the coal mine. And so this large open space in a crook of the Bow River was created by essentially mine tailings coming out of the coal mine, either rock or bits of coal that are too small to really sell, and all the sort of debris that comes with that. Right in the middle of that site, for several years, the coal mine was running a coal briquette factory, which would take coal and some coal dust and some binding agents and make into briquettes for home heating purposes. You can imagine the kind of contamination we get with the ground there. So much so that in 2007, the company that still held the responsibility for the site was notified of discovery of coal tars during some excavations and had to bring in a remediation company to build quite an extensive subsurface barrier to prevent the Bow River from essentially gradually infiltrating through the site, because in the middle of that space is some really nasty stuff. So they built an extensive soil bentonite slurry wall across the middle of that site, and you can see the excavations swallowing entire bulldozers. And you can see here just the very black dirt that they're digging up. And that's not humus, that's coal. And so when we started excavations on our site, we kind of got a sense of how they did all of this. Essentially, they flattened out all of that coal debris that came out, dumped a layer, not quite a meter of fill on top of that, and called it good. And so you can see here the striations that we get. And the first couple of feet is that kind of gray earth, and that's the fill. And below that, it becomes very black. And so that's a lot of the coal debris. We took samples from that upper layer and from that lower layer and had it tested. Because you need to for soil disposal here, because this is a known issue. And we were over limits for benzene, toluene, and selenium. We actually exceeded class 2 industrial landfill limits on toluene, but that turned out not to be soluble. But the issue there that we ran into is that our local landfill is a class 3 landfill, which essentially means clean fill only. There's no liner for that landfill, and they assume that anything put in there will eventually get leached into the Bow River. So we couldn't dispose of any of our excavated material there. All of our excavated material had to go to the Shepherd landfill on the far side of Calgary and get disposed of as industrial waste. It also led us to approach the design in a way to mitigate for this sort of ground contamination. This is the survey of the lot, and you can see that there's a high point just under 15 meters above datum, and it slopes down towards the back to lows about 13 meters above datum. So essentially what we did is site the entire home on top of the existing land. We did have to excavate for some foundation walls, but we'll get to that. The sloping site unfortunately prevented us from using a raft slab, which would have been great. But it does help with water management. Because of that sloping site, we did need some short foundation walls just to hold everything in place. But we dug excavations for those. This is excavations for the footers, and you can see we're just touching into that coal stratum. We tried to stay above it as much as possible to both limit how much of that we were getting into and how much excavated material we were going to have to pay to ship an hour and a half away. And you can see that we put in fairly short foundation walls. So this is still effectively a frost protected shallow foundation, and it depends on insulation skirting that goes the whole way around to prevent frost heave. So the next challenge is that if we look back at the photo of Canmore and we think about what's been in the news this year, we are right in a wildland urban interface. We're in a mountain valley that's extensively treed, and that gets substantial winds going down valley pretty much every afternoon. There was a controlled burn earlier this year that got out of hand up by Banff, and that's not unusual. The town's wildfire strategy report identified 119 wildfires just in the town area between 1990 and 2009. Now, the town's been doing a lot of work on reducing fuel management within the town and some fuel management breaks around the town, but there's still substantial risk. The report looked at every neighborhood of the town and analyzed fire risk. The one we're in is called Homesteads. You can see it here that the average is a high fire risk. It varies from low to extreme. So if we look at a colored map of what fire risk in the town is, you see extreme in red all the way down to low in green, and it's really varied around the town. But the town is surrounded by some pretty worrying colors there. We're right on that green patch where the black arrow indicates. So we're right by the river. We're at the bottom of the hill. We have a pretty open grassy field behind us thanks to that coal mine history, which does help with fire risk. But we can't really be confident of that because there's been a lot of work recently looking into the factors that cause or kind of underlie wildfire risk. A lot of this coming out of California in the last few years for good reason. And what that kind of tells us is that structural characteristics are often much more important than defensible space around the structure. And that's because the most flammable parts of a wildfire event are embers, which are windblown, can blow up to 10 kilometers ahead of the flame on the structural characteristics of the home. But then homes in neighborhoods, the home is the most flammable part of the landscape. And there's been some analysis of California looking at this, and there are photos showing trees which have not burned right next to a house which has burned, because a healthy tree is essentially wet, it's moist, it's full of water. It's kind of difficult to get to burn, whereas many houses, unfortunately, very much are not. So we looked at a lot of elements of design in order to mitigate fire risk. You can never really remove it entirely, but just for fire resilience. And fortunately, we were able to, again, lean on a lot of work that's been done in California around this. So we selected non-combustible roofing. So it's a metal roofing. We're selecting non-combustible siding, which in our case is a metal siding, non-combustible soffits and flashing, again, metal soffits and metal flashing, metal gutters with gutter guards, because leaf and tree debris collecting gutters is a very common source of ignition when presented with firing embers. Ember and fire resistant vents. So you can see a cutaway of that in the top right. These are now required in a lot of parts of California, and so there are numerous suppliers that'll supply these sort of things. These particular ones are from Vulcan Vents, and it's 3 layers. There's a coarse mesh on the outside, a honeycomb center, and a fine mesh on the inside. The fine mesh prevents embers from getting through, and the honeycomb is coated in an intumescent paint. So if it's exposed to the high heat of a fire, the intumescent paint will swell and close off those honeycombs, effectively closing the vent. Now, effectively becomes a one-time use sort of thing, but that's only going to happen if there is an active flame front, essentially right at your house. We've also designed the eaves with spark-resistant baffles. So behind those vents is essentially a plywood box, which then has an exit to ventilate the attic space. In the rain screen cavity around the house behind the siding, we've packed out that cavity with mineral wool, just to give a little bit more flame resistance, because flammable rain screen cavities can also be tremendously dangerous, as we saw with the tower fire in London a few years back. Outside the house, we've selected Class A fire rated decking for the rear deck, which in our case, we found a bamboo product, which was fantastic to see, because it's effectively that bamboo product or a PVC composite that will achieve a Class A fire spread rating. The deck is going to be fully skirted, again with metal, because underdeck fires are a major source of ignition, especially for people who are keeping things like firewood under their decks. All of the timber framing on the outside of the house, which we need to support some of our overhangs, are oversized. Oversized timbers will char on the outside, creating essentially an insulation layer that prevents the necessary structural core from failing and prevents the whole thing from burning. Essentially, it's like having a large log versus kindling. And of course, we're considering defensible space in landscaping. One benefit to us is because Canmore just has one fire station, and their response times are beyond, I think it's a 10-minute legislated window. Buildings outside of the immediate surroundings of the fire station are required to have interior sprinklers, which is very helpful when addressing the houses next to you are the most flammable thing. So we hope that the interior sprinklers help cut down on some of that. One structure burns, which lights the next structure, which lights the next structure, which lights us. We're also considering design temperatures. We are in the mountains in Alberta, so it gets a little chilly here. The nearest weather station is Banff, so that's where the ASHRAE data pulls from. We're looking at a design temperature in the winter of about -25, design temperature in the summer of about 25, 26. But of course, we know that climate change is changing those temperatures. There's been a number of studies looking at what future climates are like, and trying to really map it out to provide more granular data that people can make decisions based on. This is a good one in PLUS from a couple years ago. And what they did is essentially model anticipated future climates for existing cities and provide city pairs. So the closest modeled city was Calgary, And up at the top, this is from their supplementary materials. The closest cities that Calgary is anticipated to mirror in 2050 are Lanzhou, which is a city in central China, and Denver and Minneapolis. It's a lot easier to get ASHRAE data for Denver and Minneapolis, so I pulled those ones out here. And if we look at all of them together, so we have Banff up at the top, that's our current conditions. Denver and Minneapolis down below, so somewhere in that sort of range is what we're expecting in 2050, which is just 27 years from now, which is well within the time that we still expect to be in the home. And we see that we're going from a negative 26-degree winter design temperature to something like negative 15 to negative 20. And a 26-degree summer design temperature is something a little over 30, which means we're probably going to need a bit less heating, but we're definitely going to need some cooling, and we're going to need to consider cooling needs and heat gains. Then that gets us to thinking about inside design conditions. My background is in the health sciences, so this is a paper that's gotten a lot of prominence lately for good reason, from 1986, looking at the effect of indoor relative humidity on a bunch of health impacts. So bacterial transmission, viral transmission, sinus infections, chemical interactions. And what it found is that there's kind of an optimum relative humidity zone between 40 and 60% relative humidity, where these sort of things aren't as bad. And that probably makes sense to a lot of people. If you think about the winter in Canada, it gets really dry and your sinuses are much more sensitive, and you're getting colds and you're getting flus, and there's some biological reasons why. And of course, we've seen this validated quite recently. This is one particular study with just a massive N, 121 countries, from which they pulled epidemiological and meteorological data in order to model indoor relative humidity. And they found that, yeah, basically exactly what they're saying in 1986, between 40 and 60% relative humidity is much better for human health. Now, of course, if you say that I want to have my inside design temperature be 22, 23 degrees Celsius and 40 to 50% relative humidity, say that to most builders in especially the cold parts of North America, and they're going to think, oh my God, the condensation. And so that's really something that we have to consider when designing the home, is if we are going to try to maintain these sort of healthier indoor conditions, how do we do that without inducing a lot of moisture problems and building failures and just growing carpets full of mold? And a lot of that comes down to our wall assembly. And this is where aiming for Passive House standards really helps. Just the hygiene factor that Passive House often harps on about is essential in cases like this. And so our wall assembly is effectively a structural 2x6 wall with an insulation cavity outboard of that. We make up that insulation cavity using TJIs. So we have essentially 1 foot TJIs mounted vertically, defining a cavity that gets wrapped in Mento and then packed with dense packed cellulose. That means that the sheathing plywood between the 2x6 structural wall and the insulation cavity is our vapor control layer, our primary vapor control layer, and our primary air barrier. And that can get detailed and taped and then essentially buried in the wall, where it's not going to run the risk of getting punctured or getting damaged. And good luck trying to, affect a 1/2-inch plywood sheet behind a 2x6 cavity. But this also means that most of our insulation is outboard of that vapor and air control layer, which keeps that layer warm, which reduces the chances of condensation issues. We're also using vapor open insulation and materials the whole way through. So this assembly can dry to the inside, it can dry to the outside. The dense packed cellulose has substantial high girth buffering capacity, which is really great. And then, as I mentioned, as part of the fire resilience, we've packed that all out with rock wool on the outside, which again is vapor open and is hydrophobic, so that helps with the performance of the rain screen cavity. This wall assembly then gets sat on top of the foundation. So the 2x6 structural wall sits on top of the foundation wall, which sits on top of the footing. So we get good structure there. The outboard insulation cavity sits on top of the outboard insulation for the foundation, which is primarily EPS. But then that layer of rock wool is continuous all the way from the rain screen cavity all the way down to the footer, which helps deal with some of the, we're not sure about the soils around us and we don't want any of what might be in the soils to be touching the plastic foam. But was also actually very useful during construction as effectively protection, mechanical protection. So that wall assembly construction was done by Collective Carpentry at the shop in Invermere. This is what that looks like. So you can see at the bottom laying on the table is the 2x6 layer. On top of that is plywood that is then taped inside the insulation cavity. The insulation cavity is defined by those TGIs. The whole thing is wrapped in Mento. Horizontal strapping goes on to help hold it all together. And then it's filled with dense packed cellulose in the shop. The ceiling assembly is similar. We take a 9-inch TGI with plywood backing and put that on top of the structural plain 2x6 wall. That then gets taped, so we have continuity of the air barrier, continuity of the vapor control layer. We get a service cavity up in the ceiling, so we're not having to penetrate anywhere. We have service cavities effectively in all of the TGI and structural walls. And then for our purposes, that ceiling assembly was topped with Adhero on the top, which is then tied to the Mento, which goes up and over the outside of the insulation cavity, giving us a continuous outside control layer. It's also important that we choose very performant windows. We're looking at windows that are available Passive House cold climate certified, and that's a bit of a rarity. We end up going with these windows from Enersign, which are just gorgeous. They're a wood window with a structural multi-density foam on the outside. So you can see the wood, and then to the left of that, the foam, and then a lower density foam insert in there, and then they're aluminum clad on the outside. And these were great. They did a lot of custom sizing just as of course. We also got some extensions to accommodate for some exterior shading that we're doing, and some interior dados to receive interior trim, and all just clicks together pretty beautifully. It was also notable that at the time we were shopping for these, this was within about 10% of North American fiberglass or PVC windows. And so it made a lot of sense to go this way. Now, we did have to secure pricing at one point because their prices have gone up, because costs in Europe have gone up substantially. These are made in Germany. So I don't know if that pricing would hold true now, but that's what we ended up with. I mentioned some extensions to those windows for exterior shades. So we're doing exterior shades. These are from Hella out of Austria. We had tried some North American manufacturers, but we couldn't get in touch with them. And these ones, again, are custom sized for the windows. They run in tracks along each side of the window to help keep the screens in place. During wind events, we went with effectively roller shades, but they also have Venetian style and all sorts of other ones. And going with exterior shades allows us to reject that summer heat before it enters the window. And also it prevents the creation of microclimates between the window and the window shades on the inside during winter, which is something that we've experienced in our current place, especially bedroom blackout blinds where you're trying to get a good seal. You've created an air cavity between the window and the blind, which doesn't get practically any circulation. So moving that off the outside makes a lot of sense performance-wise. Putting this all together, we end up with what I always call the thermal core and then kind of an aesthetic umbrella. So the thermal core are those panels that got fabbed offsite for us with the modified Larson truss assembly. And that thermal core is a very simple shape. It's just a box. It's got a little bit of a bend to one side of it, just to accommodate the pie-shaped lot. If it weren't a pie-shaped lot, this could easily just be a rectangle. And onto that, we add a site-framed garage at one side of the house, site-framed deck at the other side of the garage, and then we add the roof structure, which is fairly complex to accommodate within height maxima, but also gives us the generous 3-foot overhangs that we're looking for in order to keep water away from the house. But it also gives us the kind of mountain design vernacular, which is expected in this area. So this is very cool. You can have your optimal thermal core, but still make it fit in. Speaking of acceptability in the area, we had an interesting time with how big the house is. So I have discovered a lot of ways to measure how big a home is. This house has 310 square meters of conditioned floor area. If you measure to the outside of the bearing walls, so the 2x6 wall, it's 320 square meters. If you measure to the outside of the siding, however, 361, because the walls are effectively 2 feet thick. The town of Canmore has a gross floor area limit for homes. This seems to apply mostly for aesthetic purposes. And for purposes of the GFA calculations, they measure to the outside surface of the home. So in their calculations, we were about 350 square meters, which was a little bit, about 2% over the limit for our lot, which required a variance. And we made that case that if we were to measure to the outside surface of our structural bearing walls, that we're only 308 square meters in their formula, which is well under the limit. This is basically looking at the difference between a code-built house and our passive house. But this effectively means that the town of Canmore has a local bylaw which encourages the building of thin walls and the building of basements, because basements are not counted for this GFA calculation. We have thick walls and no basement, so that was an issue for us. But fortunately, we were able to make a case that our higher energy performance aligned with the town's goals and get that variance. We also encounter a little bit of friction talking to regular people because the house looks fairly big from the outside. It has thick walls. It has an energy heal truss for the roof. It has a lot of space in the attic for insulation. And so it looks bigger than you'd expect for an floor space. So it's for the amount of interior floor space. If you were to measure for real estate purposes, we're 3,400 square feet. But real estate purposes don't measure basements. An equivalent 2-story home with a basement would get sold measured at 2,300 square feet. But this is just, it's been a point of discussion. As I mentioned, we used offsite construction for the main panels. This is built by Collective Carpentry in Invermere inside in their shop. They're building this in, I think we are in end of December and January is when they're building the panels. So I felt a lot better not making people frame outside in that weather. And they could do everything at convenient tabletop height, which is just a lot better for everyone's backs and muscles. I felt a lot better about that. Everything arrived on 3 semi-trucks and got craned into place. Unfortunately, the week of install that we picked ended up being a very cold week. So I'm very appreciative to everyone who was working outside in that cold. One interesting thing this led to is some sequencing challenges. We did not have the interior floor poured by the time we had the panels going up, and the design relies on some interior load-bearing walls that you can see here. So the crew at HSS, and I think it was Robert's idea in particular, came up with the idea of putting some lolly columns in the middle to carry beams, to carry that interior load. And that was done by pouring some pad footings when we were pouring the rest of the foundation, as seen there. Then the base of the columns got placed and aligned, and some PVC pipes placed vertically on them with strappings just to hold them in place. That then got buried underneath the fill for the inside of the home, and the lolly columns placed. And then the panels were brought in, the beams and the home built around that. And then the subslab foam, subslab vapor barrier was placed around those columns, and detailed around them. And then the slab was poured. And then once the slab was poured, the interior load-bearing walls could be framed. Those columns could be cut away, pulled out. So now all there is a PVC tube that goes down all the way. And one of the guys spent a while with a hole saw making little rounds of rock wool that then got stuffed into the pipe. So the pipe is now insulated. But this was a really great idea, which prevented delays because of sequencing, but also prevented us having a great big thermal bridge right in the middle of the floor. So try to run through here quickly. We were thinking about what to do for space conditioning and whether we would essentially where to heat sink to. We're going to use a heat pump, but is it going to be air source or is it going to be ground source? So there's some data looking at essentially how heat demand changes with outside temperature. And we see that it's not linear. As outside temperature goes down, heat demand goes up substantially. We also see that the COP of air source, or well, any heat pump drops as the temperature difference that you're trying to accomplish increases. So with an air source heat pump, we'd be looking at about a 60 Kelvin temperature differential inside to outside versus a ground source heat pump in this area, we'd have like a 30 Kelvin delta. And so there's a substantial difference in COP. And when you put the two of those together, you start thinking about, well, how is this impacting the grid when you're suddenly having to pull much higher load at a lower efficiency? And this study modeled homes in Toronto and Vancouver and modeled air source and ground source heat pumps. And it's basically what you think. The air source heat pump not only needs more electricity, but you can see in the box plot on the left there are times when it is pulling substantially more because those are your cold days. So it's not just the average over the season, but those cold design day peak load conditions, when everyone is pulling hard from the grid, you're pulling a lot more than you would be with a ground source. And that's what led us to go ground source, because that's sort of the generation that you get under those conditions is just the dirtiest peaking power. So we put two boreholes in the back. We were hoping to hit water and do an open loop, but what we found was coal, which is not surprising. That was more to get rid of. And then as far as distribution, we just went air. I was going around thinking a lot about hydronic distribution, but our heat load is so low, it's about 5,000 watts. And altogether, the entire house is spec'd out for 600 CFM. So air was just the easy way to do that. Talking about air quality is a real issue. This summer, we've seen some really bad smoke days. The WHO says that your 24-hour air pollution limit for PM 2.5 should be under 15 micrograms per cubic meter. The EPA in the US says 35. Health Canada refuses to even be drawn on a number. But this summer we had 23 days in town with PM 2.5 concentrations above the EPA limit, 35, and we had 66 days above the WHO limit. So that makes filtration really important. Just briefly on the ERV, our ERV is from Tempeth. It's a dual core design, and essentially airflow changes every minute going into and out of the core. So one core is always being energized while the other core is being de-energized, and then they switch. You can think of it kind of like the Luna sort of through wall, just having two of them, so there's constantly fresh air coming in. That also makes it really easy to do summer bypass. Coming back to that filtration, we have an air handler because we're doing air distribution, and that lets us put a very good filter onto it. The HRV can also be equipped with filters, and then as needed, we can run air cleaners, and that's just something that's required these days. One fun thing, kitchen ventilation is not exhausting to the outside. It's going up and over and into the pantry and then to an inline filter box where it goes through a secondary filter. Domestic hot water is being supplied by a heat pump hot water heat pump water heater, and that is exhausting its cold air directly upstairs into the pantry to give us a chilled pantry, which is kind of fun. And there's an on-demand hot water recirc line for one side of the house so that we don't constantly run a recirc. We are designing the home for PV. We have a lot of space to put PV panels, and we're putting main electrical panel in the garage for that. And there's space for the DC panel, the batteries, the inverters, EVSE out there as well. Net zero, we're aiming for net zero site energy over an annual period. There's a lot of squishiness around net zero definitions. But we're trying to get our load down first, and that's the important part of Passive House, rather than just throwing on more and more panels. Just briefly about embodied carbon, we did try to minimize the amount of concrete we're using, so slab on grade, short foundation walls. But of course, we were challenged by some of the site slopes there. We limited the amount of structural steel we have as much as possible. It's mostly just in the exterior deck, which is again needed for fire purposes. You're seeing kind of a balancing theme here. Siding, because we need non-combustible siding, that's metal, that's cement, that's masonry. Take your pick. We went with metal because it's recyclable. Insulation, we're mostly cellulose above grade, EPS below grade. That options we're currently looking at. Wood fiber would be nice, but I know that the main plant is running a little behind on their plan. Most of our acoustic treatment inside is wood fiber though, from Sonopan. And the decking, like I said, it's a high density thermally modified bamboo, which is nice just because the other fire rated decking products are generally PVC. We're also accommodating for future needs with an elevator that's been roughed in, low sills for all of the doors, and service cavities, as I was mentioning, pretty much everywhere to allow for remodelability. Just as a little bonus at the back, there's this really great paper that came out like a week ago in Nature, and some archaeologists that found structural wood use that dated to 476,000 years ago, which is 100,000 years before the evolution of Homo sapiens. So, as I was joking with Kim, sometimes permanent wood foundations really are permanent. All right, that's all I got. Happy to answer some questions now.
Great. Thank you very much, Edmund. Lovely house, well thought out, well designed. There's some questions submitted previously, so maybe we'll go through some of those. If the people have questions, you can either unmute or put in the question box. But I guess, so you're not actually, you haven't lived in it yet, so we can't, I guess one of the questions was is what's it like living in a passive house? But I guess what are you looking forward to maybe on living in a passive house?
Yeah, I think that the best example is this summer we had some really hot days. And this summer the walls were up and most of the windows were in, but the attic ceiling was not insulated. And there were no mechanical systems running because we're just starting. Could drop by site and it would be nice and cool inside the house. It would be blazing and 30 outside, and it would be just a little bit chilly on the inside of the house. So I think that sort of comfort is the primary thing that would be nice. But also some lower bills. We did not connect a gas line, which means we won't have even the monthly charge for gas, which I think is amounting to about $50 a month these days, which just not having those recurring bills is nice.
Excellent. There was one good photo on it, but there's some questions on kind of how you tied in the underslab air barrier to the ICF foundation. And if you want, I think Kim is here. She could probably answer it. I could also kind of give some answers on how you do it, but do you want to take the first crack at it?
Yeah, I can take a crack at that. So for underslab air barrier, the underslab air barrier ran up the ICF foundation wall, so it's basically just polyethylene, and that got taped then to the blue skin that capped the foundation, just ran over it into the manto. So it's essentially just the red line test of never lifting your pencil and making sure that each layer is taped to the other one. And for penetrations of the subslab air barrier, those were all taped using the supplier's tape. I think we used Perminator polyethylene, and there is a tape that comes with that, and that was just taped around each of the penetrations.
Yep, and generally you want those tapes to kind of be stretchy, so that you can make sure that you allow some movement between the two different things. But yeah, basically just taping your penetrations. Bit of did you break down the costs kind of the closed loop ground source heat pump? Because
Yeah,
that's obviously the trade-off always between air source and ground source.
absolutely. Oh, Kim's here and can probably comment more about the air barrier, but cost for ground source for us, it was about $36,000. That is in our market. And that's everything up to the ductwork. So that is the
That's
drilling, that is the loop, that is the heat pump, air handler, and everything. So it was more than air source, but not that much more.
no, your air source equipment would probably be somewhere in the teens. So yeah, a little bit more, but not a ton. Kim,
Yeah,
you want to
yeah,
unmute and add anything?
Yeah, so first thing I'm going to say is I think I'm going to get Edmund to do all of my presentations going forward.
Yep, yeah, he's pretty good.
And about the sub slab joining to the side of the weather barriers, we had a lot of discussions about it. And I just wanted to bring that up. The fact that I had an idea, the contractor had an idea, then that the wall suppliers had an idea, and we went back and forth on a few ideas. So I wanted to bring that part up just to say that everybody's ideas count. There's no right way to do one thing. There's a lot of options to do it. So I mean, this ended up being the easy thing to do, mostly because of the temperature. And it was quite simple. And in terms of the boreholes, there were only 2 boreholes. That makes a really big difference for the geothermal. So we only needed 2 boreholes because we are such a low load for heating. And that again says building envelope first, other things next. I think those were the 3 points I wanted to make right now.
Yep. I guess maybe one thing question I would add is could the ground source heat pump also do your domestic hot water, or is that too much complication and that's why you went with the heat pump hot water tank?
yeah. So
Yeah, yeah.
I can
Go.
feel that. So
Yeah.
yes, you can do that. Typically, the way that's done is that the air handler heat pump unit has a DC superheater, which essentially preheats domestic hot water. Most of those cases, it is just a preheat, and it's not going to do all of the heating. I'm sure there are products in the market that'll do full water to water, but it becomes just so much more complicated. Because you'd essentially be having 2 heat pumps sharing that loop. Also, one complication there is that our load is so low that our heat pump is a 2-ton unit, and that is too small for the manufacturer to include that de-superheat tie-in for domestic hot water. So it ended up being much simpler, essentially just to couple them via the air. And again, that gave us the benefit of taking the cold air coming off of the heat pump water heater and putting that into the pantry and essentially cooling the pantry. But yes, it's possible. It's just with the current product that we've seen on the market, it's much more expensive. And yeah.
Yeah, and if you can definitely find a use for that cool, dry air coming off your heat pump. Hot water
Exactly.
tank, that's an excellent way. Yeah, your cold room or your cold pantry is an excellent use. So for, I guess, public infrastructure, so I think you told me you had a 200 amp service. You might have been able to get away with a 100 amp service had you really tried. You have no
Oh, yeah.
natural gas connection, and you're tied to the water and sewer.
Yeah, and honestly, the reason we went with a 200 amp connection is just to maximize the amount of solar panel that we'd be then allowed to have. Yeah, right now we're currently in a place with a 100 amp connection. It is a gas furnace, but there is an air conditioner in there. We have an EV that we charge off of that. We have an induction cooktop that we use. We have a heat pump dryer. Heat pump dryer is a great way to save about 5,000 watts in your load calcs, and a whole bunch of interior air going to the outside. But it's definitely doable with a smaller connection. I'd say one other thing that we considered, and I kind of touched on this briefly, is that we were considering the impact that our mechanicals choices have upon grid loading. Just because, again, going to air source is much less expensive up front, doesn't require the drilling. Some places you're not going to be able to do the drilling. But because of increasing load combining with increasing, or rather decreasing efficiency, the amount of power draw is just substantially higher in those peak draw events. And those peak draw events are probably coming from peaker plants, which are just the dirtiest. And so that is something that we are definitely considering. We also do some time of use internally. I mean, the EV we have, we can tell it just to charge overnight. And so right now we just have a charge overnight and avoid the evening peaks, because those are, again, the dirtiest and the highest grid events. So planning on doing a little bit more of that as well in the house once we have solar to add to that arbitrage.
Excellent. Do you mind or want to talk a little bit about construction costs and any?
Yeah,
Everyone always asks.
construction costs have been going up. And so I don't even know where we'd be at for, anyway, we are probably 25-30% higher than when we initially started kind of figuring things out. So things have gone up recently, but things are also just in motion a lot. Wood prices went up and then when we went down, and so we were a little lucky that we did a lot of wood purchasing when they're on their way down, but they're now down farther. We were a little trepidatious looking at shipping costs because for a while their shipping costs were extremely high when we were bringing over a container full of windows from Europe, but by the time we did bring them over, shipping costs had come most of the way back down. And so we're seeing things that are a combination of inflation in general, excessive demand in the building sector. We're seeing increased costs of some of the inputs. Like I mentioned, we secured pricing with our window supplier before their prices went up, I think 25%. And so they were dealing with increased energy costs in Europe because of the largest land war in Europe in a century, combined with record hot summers, which have reduced electricity output from thermal plants that need that water for cooling purposes, and have increased shipping costs in Europe because river barges now can't carry as much because the river water levels are lower. So it's just all of this stuff together. Even back to that hard freeze that Texas had a few years ago, there are a lot of chemical supply and glue and adhesive suppliers who have their factories in Texas because of lax environmental laws. And what happens when you have a glue plant that encounters sub-freezing temperatures that was never designed for, and the power goes out, is that it freezes solid. And then you knock it down and you build a new glue plant. And this has a knock-on effect on prices the whole way through. Yeah. So it's a challenge and it's a moving target.
Yeah. And then most of those cost increases would be regardless of whether you're doing high performance or code minimum.
Exactly. Yeah. And there were times when in the last little while, plywood was less expensive than some of the commodity OSBs that were more reliant on those adhesives. And so it's difficult to say. And I will say, as a homeowner, it's a little difficult to fully get your head around because nobody actually knows what the prices of anything are. Even the contractors and suppliers. What you have to do is you have to specify something, have it quoted, and then that quoted price is good for a week or two. And before you had that quoted, no one knows. So it's a little bit of feeling your way through in the dark.
Yeah, and Canmore in general has a higher construction cost and higher commodity rate just because you're further away and in colder areas. So yeah,
we're further away, and labor costs in Canmore are substantially higher because housing costs in Canmore are incredibly high. It's the most expensive market in Alberta. So if you're going to hire anyone to work here, they need to be able to live. And you just have to pay wages that are, good and living wages for the people who are working here. And that just happens to be higher.
Yep.
I just want to add one more thing that Edmund skirted in that whole realistic discussion about costs. But one thing that people will ask, well, what's this cost per square foot? And I think Edmund's awesome slide about how difficult it is to tell you how many square feet this place is, because it depends on what standard we're talking about. And if we are talking about how much what the standard is by the real estate standards, is a completely different number than when we're going to be outside of the building. So I think that's something to keep in mind when we're building houses and buildings with really flat walls.
Yeah, and whether or not they have basements or don't have basements, and yeah,
all those things.
the per square foot of houses is
How
very
many
difficult.
bathrooms you have?
Oh yeah, yes,
And-
because
And empty-
and also when you have a really high ceiling in the garage, which when you walk into this house, people reflect on that one a lot. So there's some interesting details within the house that might contribute to the cost. But what people in general are looking for is how many bedrooms and how many bathrooms. And that is not at all how how you would look at a building like Edmund's, which is really custom. Edmund and Monica, sorry, I correct myself. It's very custom, really about their lifestyle, and can't be judged in a normal way almost at all.
Oh, and I will say it's also our office. So
Yeah.
a substantial portion of the second floor is office space for us because that's where we are all the time.
Excellent. That's mostly the pre-sent questions. Any other questions from the group? Either unmute or stick your hand up. No? Well, and then with that, we are pretty much right on time. So thank you all for coming. Thank you, Edmund, for sharing your excellent house. The next month's Passive House Alberta Coffee Talk will be with Beyond Code and kind of the different types of high performance details that they can provide. And oh, I see a question. Mark, you got a question? Feel free to unmute.
It wasn't a question, it was clapping hands for applause.
Oh,
Thank
perfect.
you. As Kim said, a wonderful presentation. And since I've opened the mic, it was about 12 years ago that I met Kim, and she designed a house for us that never got built, but she got involved with Passive House. And so I want to, in her listening, pat her on the back for what she's achieved over the last 12 years. So thank you, Kim. Thank you, Edmund, for what a wonderful presentation. And thank you, Frank, for the masterminding this coffee talk.
Excellent.
Thank you. Oh, that reminds me, since we just have a minute, I feel like I should tell the story of how I found Kim. When I was first looking to do a better than code house, I was trying to figure out what does that mean and where do you find someone to help with that. I went by SAIT for they have a high performance building lab, and they had a tour, and I asked there and they didn't know. They suggested Googling, which is what I did. And I ended up on the database of certified passive house professionals and looked for Alberta. And in Southern Alberta, I think at the time it was Kim and it was Frank. And I was pretty sure that Kim was the only one who was working as a designer at the time. And that's how I found her. So for anyone thinking about getting your passive house designer certification, getting into that database, there are some people who that's the only place we can find anyone.
Yep, yeah, it is definitely a growing market, and still there's more names on that list now, but not a ton, and definitely room for more. Alrighty, well, I think I will end the recording, and thank you all. Have a good day.